So to finish off this section, we've got this idea of the natural number. Now this is going to seem very strange. Uh, why would we call this the natural number? This number is very weird. So we designate the natural number with the letter E. It turns out the number we're talking about is it's 2.7182818.284 dot dot dot. The decimals continue with no pattern. The natural number is a very similar number to pi, right? It's got this decimals going on forever with no pattern to it. Here's where that number comes from, and this probably isn't gonna clarify much until we see where this is going. If you take this expression, 1 plus 1 over n raised to the n, and you start plugging in values of n getting larger and larger and larger, then for very big values of n, the result will come out to this number that we call e. So what a strange idea. If we were in class, there's kind of a fun activity you can do. Very simple. You just plug in values of n that slowly get larger and larger. So you start with n equals 1, plug that in. Then maybe you plug in n equals 2. Then maybe n equals 5, n equals 10, n equals 100. You start getting bigger and bigger and bigger. And you would think, like, oh, well, the exponent, if that exponent gets bigger, it's just going to become huge. But then at the same time, because you're adding 1 over n, you're adding values that are getting smaller. So this is getting smaller, but this is getting bigger. And it turns out as the values in bin get bigger, it balances out. Like this is pulling it up and this is pulling it down, and this tug of war ends up resting on this strange number that we call e. So what's the point of that, and how in the world is that natural? Okay, so well, I guess a little bit more before we see that part. This number e is so influential and so important that if somebody, we talk about exponential functions right earlier in this section, but if somebody ever says the exponential function, capital THE, what is the exponential function? It's always a base e. E raised to the x is the exponential function. And that probably gives you a hint at why we call it by the letter e, because it connects with exponentials. There's some other history on other reasons why we might get the letter E for this, but this is an easy one to remember because there's this like a very heavy connection to the exponential growth, in fact. Okay, so where is this going? So an application that we're going to look at here in this first section is compound interest. And that's a really good way to look at exponential growth, right? You invest some money, it gains interest, and you just leave it in the bank, or you leave it gaining its interest, and it just grows and grows, and the more it grows, the faster it grows because there's more money in the bank. So here's the equation. I know I got these arrows all over the place, but it's A equals P times the quantity 1 plus R over N, and then that is raised to the NT. And I'll just explain what all these parts mean. So A is the amount, so that would be the amount after some number of years that it's just been gaining interest. We use the letter P because it represents the principal. The principal is always the initial amount that you invest. Although I see that word much more often when it comes to loans. The principal of the loan, that's the original loan amount that you're trying to pay off, and interest is working against you, right? Okay, anyway, the initial amount, the principal. R is your interest rate. R Usually they tell us in the problem R as a percentage, but so we want to convert that to a decimal before we plug it into the formula. We'll see that in a moment. N appears twice. N is here, N is here. N is the number of compoundings per year. So how many times does our investment gain interest? How many times per year? So a lot of times it's monthly. So if we gained interest every month, then that would be 12 times per year, and we'd put 12 in. But sometimes it's different than that. And then finally, T. Well, T, it's time, but specifically it represents years, and it's always going to be years in the compound interest formula. Okay, so let's see an example. Here we go. Let's keep that. I'm having a hard time keeping that formula on the screen. Okay, I think that works. Let's say $8,500 is invested at 5.5% compounded quarterly. What is the amount after 12 years? Okay, so we got this $8,500. Who knows where it came from? We just stick it into this, maybe it's a mutual fund, like in the stock market or something. I don't know. But whatever happens, it gains 5.5% compounded quarterly for the entire 12 years. Okay, great. So we've got a nice formula for that. We know we're trying to compute the amount A. So we need to figure out what is the principal, what do we plug in for R, for N, and then finally for T. Well, I'll just show you guys. If we were in class, we would talk through it all piece by piece. But here it is. So the principal is that $8,500, the initial investment. Then the formula goes parentheses, right? 1 plus. And then here's our interest rate. So we convert that percentage by moving the decimal, right? 2 places. 0.055 over, and here's the N. It's compounded quarterly. So how many times is that per year? Well, that's 4 times per year. A quarter, right, is 1/4. So 4 times per year. So the 4 appears there and again there. And finally times 12 because it's 12 years total. Okay. So what you'll do, I recommend just go for this in one shot in a calculator. Some people like to multiply that exponent. That makes it a little bit easier to do the calculations in the calculator, but I'm just going to show you what I would type here. I would type in 8,500 parentheses 1 plus 0.055 over 4, just like that. And then that's going to be raised. And I said, I kind of like, let's just go ahead and multiply that. Make sure that our calculator knows that both these should be up in the exponent. Well, 4 times 12 is 48, so we're just going to raise it to the 48. And okay. And I'll just hit enter and do that whole thing. And I got 16,371.955. Okay. This is going to be a dollar amount, so I'm going to round that to the nearest cent. And I'm going to write this. 16,371.96 when I round up that penny. And of course that is dollars, so maybe I'll throw the units on there, the dollar sign. Not too bad. We turned, I don't know about I guess, but the 8,500 turned into over 16,000. It got pretty close to doubling. Now it took 12 years of just sitting there to do it, but not too bad at the end of the day. Okay, so where does the natural number E come in? So back in that formula for compound interest, we saw 1 plus, it's R there, but 1 plus 1 over N raised to the N is where E comes from, right? Okay. So here we go. Another way to compound interest is called continuously compounded interest. And what that means is the number of compounding periods is infinite over the course of the year. Like, what is that? How can the number of compounding periods be infinite, right? So the last one we did was quarterly. They earn interest 4 times per year. Okay. Well, you could make it more, right? So if we compounded interest monthly, that'd be 12 times per year, n equals 12. You could compound interest daily. That'd be n equals 365. But why stop there? You could compound interest every hour, right? Or every second. Or you could get to the point where there is no gap between one interest moment and the next. That money is just constantly gaining interest at every given moment. There's no, times when it happens. It's just always gaining interest from one moment to the next, to the next, to the next. We always introduce continuously compounded interest when it comes to investments. That's just a natural progression from compound interest. Truth is, continuously compounded interest, you never see that in the real world with investments of money, but you do see it and you can model it really well when it comes to like population growth, because populations gain, large populations are gaining, I don't know what, I don't know, like people, or if it's bacteria multiplying, or animals, species, they're gaining population size at pretty much every instant, right? I mean, all around the world there are babies being born, right? Or if you're studying a bacteria that's growing and multiplying, well, any given moment there's probably another one springing up. So but we learn it in the context of money, so we'll just accept that for the practice. So yeah, so the number of compounding periods is infinite. It's just always happening. So what does that mean for our formula? Our formula gets really, really simple. So before, let me just so we can compare, we had A equals P 1 plus R over N to the NT, right? So we can see in it the 1 plus 1 over N to the N. And we're saying that N goes to infinity, right? So this is the E right there. Well, all this stuff here, the 1 plus 1 over N to the N, all of that just became E. And it just so happens that the way the mathematics works out, that R jumps up into the exponent of E. And I'm not going to explain why. Turns out that's actually rather advanced, why that R jumps up into the exponent. So at the end of the day, there's your formula. But we can see the E. That's pretty cool. All right. So now, even simpler, right? That's the amount. There's our principal, our interest rate, our time. E is that number, and it's a number in your calculator. And I'll show you where it is in a moment. Let's look at an example. So we're going to use some familiar numbers here. $8,500 is invested at 5.5%, compounded continuously. So now what is the amount after 12 years? Okay. So same principal, same interest rate, still 12 years, but now we compound interest every given moment. So let's take a look. We got our principal, right? E raised to the R, converting to a decimal, T. And I'm just going to grab my calculator right here. And I'm going to say, all right, 8,500. E, and I know it's really, really blurry, but on my calculator, it's right there. So if I just type that once, it does it. And it immediately has me type in an exponent to E, because that's pretty much the predominant usefulness of E, is putting powers in it. So I'm going to say, okay, 0.055 times 12. Now, if you've got an older calculator, you want to go ahead and put parentheses around that exponent, because it might not read it correctly. if it's not like writing it up above like that with the way these new calculators. Oh, that's a little bit clearer. But if you've got one like mine, you don't need the parentheses, but hey, better safe than sorry. So I'm going to go ahead and hey, there we go. 16,445.73 is our answer if you round to the nearest penny. And so there it is. There's our final answer right there. Now, if you compare that answer, that value, to the value we got before when we compounded quarterly, what was that answer? It was like 16,371.96, I want to say, if I remember correctly. So we squeezed a little bit more money out, like $74 or something. We squeezed out more by compounding continuously rather than quarterly. So a little bit more interest came out of it. Okay, well that concludes 10.2. So I just want to leave you guys with these problems to practice. So if we were in class, this is what I would be putting up on the screen. So I won't read it. I'll invite you, hey, just pause the video here, try them out, and in part 4, we will do these together. But you give it a try first, see what you got. All right, I'll see you in the next part where we do these together.